Cool. Let's make a start. Hey everyone, welcome to this talk. In the next 45 minutes or so, we will be talking about DLL hijacking and how we can make that even more fun by throwing environment variables into the mix. I will briefly introduce myself. My name is Wietze. That's a Dutch name. I'm originally from Amsterdam, but I now live in London, in the UK, where I work for CrowdStrike. I've presented before at other conferences, for example, the sister conference in London, as well as the one in Rome more recently, and at DEF CON last year. But enough about me. Let's talk about interesting stuff, DLL hijacking. So just the structure of this talk. We'll first start by talking about what DLL hijacking is, because not all of you may be aware, and just to make sure we're all on the same page as to what it means. A quick recap of what that is. Then we're going to move on to environment variables, and again, sort of a reminder, what are they and why do we have them? And then I'm going to bring the two together in a more attacker scenario. So bear with me. DLL hijacking. Like I said, some people use different definitions, so that's why I thought it's good I give you mine, so we know what we're talking about. To me, DLL hijacking is the tricking of a legitimate or trusted executable into loading an arbitrary DLL. Now you may be thinking, if you're new to this, you haven't heard of this, why would you want that? Well, libraries or DLLs on Windows are these shared pieces of executable code that programs may load into memory in order to use shared functionality. Now, rather than compiling your own malware executable, which is one option, you could also compile this DLL. And if you trick a legitimate DLL into loading your malicious code, you can leverage or piggyback on the trusted or reputable reputation of this program. And that means that very naive AV or even EDR software might not see it. If you use allow listing software, like Microsoft AppLocker, for example, this could be a way to bypass it. Right? So you have a legitimate executable that's trusted somehow, zero detections on virus total, and you trick it into executing your evil stuff. Now, this is a more generic term for specific subtypes. Some of these you might recognize. If you know DLL hijacking, you no doubt will have heard of DLL sideloading. I think that's by far the most common type of DLL hijacking. Basically, what you do is you need a vulnerable executable. You move that to a folder that you control, like a temp folder or, I don't know, the download folder. And you move that alongside a malicious DLL. The vulnerable executable will just simply load the DLL from the same folder it is in. And again, you have this trusted application executing your malicious code. Another one, I think these are often confused, is DLL search order hijacking. Now, I won't really be talking about search order hijacking today, but just as a reminder, in Windows, if you specify a DLL you want to load as a program, but you don't specify the full path, you just say name.dll, then Windows will try and help you by searching in a number of set locations. It will first try the same folder as the executable, and if it's not there, it will try the System32 folder, the system folder, the Windows folder, and so on. Search order hijacking, as the name suggests, makes advantage of that by putting a DLL anywhere in this order of locations before the legitimate DLL. So rather clever, but in practice, I don't see this very often. There's a number of documented cases, so it certainly exists, but compared to DLL sideloading, it's like DLL sideloading is way more popular. Another common one that you would almost forget is substitution. You literally just take a legitimate program that loads a legitimate DLL, and you replace or somehow proxy the legitimate one with a malicious version. You will all remember Stuxnet. A very crucial part of that attack was replacing a DLL in the System32 folder with modified code that partially relied on the legitimate version, but also loaded malicious code, which ended up changing the nuclear reactor's actions. Now, three more honorable mentions before I move on to sort of the problem statement. Phantom DLL hijacking. Sometimes programs try to load DLLs that don't even exist. This sometimes is the result of a dependency that was changed. Typos are even common. So that's even better, because if the DLL doesn't exist, You can place the DLL anywhere in that search order, including the path environment variable, and it will load your code. So sometimes this is even CVE worthy if it's a really trusted application or it runs with higher privileges. But yeah, that's not a good one. Windows side-by-side hijacking, or WinSXS. This is really rare, but I do want to mention it because the MITRE attack page for Windows side loading for a very long time mentioned this as like the prime use case. I think the confusion comes in because it also contains the word side, right? Windows side-by-side, which is a very specific technique in Windows. It's a compatibility mechanism for loading all the DLLs. I personally have only seen 1 or 2 documented cases. I think it's really rare, but I do want to mention it just to make sure you don't confuse the two. And then finally, it's just sort of like a catch-all bucket of input-based hijacking. This is anything that involves changing like the registry or the command line. And by changing that, you somehow trick the vulnerable application into loading your malicious DLL. Some people call it DLL redirection. Right, so we've talked about 6 types. There's a few more, but I think these are the main ones, and you might have experience with some of them. Now, from an offensive perspective, right, the problem is that these are very well documented and very well researched. If you want to learn more about any of these, just Google it, and you will find plenty of blog posts, code templates, and whatnot. So you can really get started if you want to abuse this. And that means, from a detection point of view as well, because of all this information we have, generally speaking, this is pretty well detected, all of these types. So the question is, can we come up with something new that relies on the same principle, right? Malicious code, trusted software, somehow gets executed, that bypasses the limitations of the existing types. And you've guessed it, this is where environment variables come into the mix. I will just briefly give a background on what they are and why we have them in the first place, because it's actually quite an old mechanism. And then we're going to move on how we can use it for DLL hijacking. So it's a bit, I've always found it very strangely named, environment variables, but it's basically a global variable, right? If you've done any coding, you know the concept. It is a variable that you define somewhere in your operating system, typically, that can be accessed by any part of the OS or programs running under it. If you've used Windows or Linux, you will know from bash scripts in particular, right? If you use the terminal or the command prompt, you will know the pattern $ variable name $ on Windows, or percentage sign, whatever. And then on Unix systems, you've got $ and then the variable name. So they're quite useful. You can set these in scripts or again on operating system level and then use them further down the script. What you almost would forget is that you can use them in programs as well. So any program can access these variables and use them in the code to change the flow of the program. So in C, you can use getEnv, name of the variable, and you will get the value of that variable. Typically, these are stored as strings, and most often ASCII strings. So you can store, of course, Booleans or numbers, but you would have to cast them yourselves. They're not typed. Everything is a string. And this is cross-platform. Now, I don't want to change this into a proper history lesson, even though this feels like a lecture with this auditorium. Anyway, but I do want to quickly remind ourselves why we have environment variables, specifically in Windows, because it's a bit weird. As I mentioned, environment variables are old. As early as version 7 Unix, it's the first time in an operating system we had, our mainstream operating system, we have environment variables. The problem they're trying to solve is that there's lots of repetitive information that programs use, and you don't want to bug your user every time asking the same questions. For example, what is your username, or where is your home path? So they came up with this system where you just define them once, and then every program will know, hey, if I use $user, I will know the username, or $home will give me the home path. So it's a pretty clever mechanism, and for these early day programs, it was a godsend. It made stuff a lot easier, and because you could define them yourself, it made for a lot of computer users life a lot easier.
In fact, it was so popular that only 4 years later, PC-DOS 2.0, which would later it will form the foundation for Windows, would also include it. This is a little excerpt from the release notes, the documentation, and it's remarkable how it's pretty much still the same in 2023. So it says, environment variable is a special case of a replaceable parameter. In the command prompt, use set, and then name of the variable equals value. So that is pretty much still how you do it. Percentage signs for using it in scripts, unchanged ever since. So this is 82. And then exactly 10 years later, we get proper Windows, right? Where it starts looking like the Windows we have today, Windows 3.1. That comes with the Windows registry. Now, if you've ever used Windows, you will know the registry, which is this central store of all sorts of operating system settings, program settings. And when you think about it, it's basically trying to solve the same problem as environment variables, right? It's a central place where you have all these things like usernames and paths, but much better, because registry, unlike environment variables, is typed, right? You have different types, you have hierarchy, you have permission schemes, so it's much, much better than the old school environment variables. And the registry has evolved over time, of course, but when you think about it, in Windows at least, you wouldn't really need environment variables if you had the registry, right? But there is edge cases, but for the problem it's trying to solve, the registry is actually pretty good for that. And what we see ever since is that the environment variables somehow always end up in CVEs and causing vulnerabilities. You might have heard of this path environment variable. I'm not really going to talk about it today, but in the past it has caused lots of trouble. This is something I found on a message board. It's the oldest I could find, 1997. Someone complaining about how this works and how Microsoft is unwilling to change something about it. And he writes in frustration, why would any other application developer bother to support secure configurations if this is what they see coming out of Redmond? Well, we'll see later what the people in Redmond did. And then close to the start of the millennium, the first ever CVEs were issued, and as part of the first batch, there was actually a privilege escalation issue that involved environment variables. So, long story short, it solved a very legitimate problem, environment variables. I would argue in Windows it's been replaced by something that's more robust and more flexible. But what we see is that over time, it has caused lots of issues, unforeseen things. So how are they implemented in Windows then? Because before I was just talking generically, right, cross-platform. How did they work in Windows? So all environment variables in Windows, and out of the box you get quite a few, they're all concatenated into one massive string, which has an upper limit. It can contain 33-ish thousand characters in total. So the names of your variables and the values they hold should not exceed that. Now you might wonder, right, so how does Windows, where do they store environment variable data? Because they're still there, they're still used, but where are they stored? So ironically, they're stored in the registry. So this is a table that shows in order where it gets the values for the environment variables from. So when it boots your computer, the first thing it does, it goes to the all user hive, HKLM. It will try and find all the defined variables there, and it will set them for your entire operating system. Like even prior to logging in, it will set the data there. Once you log in, it adds or even overwrites these variables based on your user-specific variables. For example, your username, right? That's a good example. That's something on user level. So once you log in, it sets user to your username. There's also something called current session. Again, not really going to talk about that today, but I do want to mention it. It is something where you can set an environment variable, and it will live for the duration of your login session. And after you log out, it's gone. Now, the most interesting thing, and this is where the DLL hijacking will come in, is the process level. So interestingly enough, environment variables are a global variable, but every process has their own table with environment variables. So every process knows what they are, but in theory, they could differ process to process. So if you know a bit about Windows internals, every process has a process environment block, the PEB. This contains all sorts of metadata about the process that's running. And if you look in the process parameters block, lo and behold, we see a number of interesting things there, like the command line, where does the standard in, standard out goes, but also the environment block. And on the right-hand side, you see what it is set to in my lab. So you see my username there a few times. You see a couple of interesting paths, like my home path. You can see that my C drive is where I installed Windows on. So the interesting thing is that every process has this own list with variables and values. That means that if you start a process, typically, it just passes down the environment variables that were set by the parent process. So if you computer boot, you get an Explorer process. If you start any new processes from that, most of the time, it will just take whatever the variables of Explorer.exe were. So it's just one big chain of processes that keeps passing on these variables. But you can overwrite it. So if we look at the Windows API, this is one way in which you can start a process. And it has an optional parameter called environment. And you can actually pass your own variables there, which means that if you start the process, it will have different values and variables and values than its parent. Right. So I hope we all have a cybersecurity mindset, right? I hope your gears start spinning. How can we use this to our advantage? How can you break something with this? So when I started looking into this, I thought, let's look at these variables. They are interesting because these are paths we normally don't control, right? Imagine you have initial foothold, you don't have any additional privileges yet. You can't really write to C/Windows or any subfolders like System32, or not any interesting ones anyway. So could we start a process, maybe change some of these variables, and then have fun? So that's what I did. I chose one of these environment variables. I then changed them to a different location. I would then start a process with these updated variables. Look in Procmon, see with this manipulated run, if I could see any different behavior. And hopefully, if it loads DLLs using an environment variable, I might trick it into running my variable. So it's visualized on the right there. Normally, this trusted program might use a variable to load some DLL. I hope you can see it if it's not too dark. But basically, it normally goes to C/legitimate path. Then in a manipulated run, I start the same process, but I overwrite that special variable with my evil path. And then if I'm lucky, it now loads my version of some lib in my manipulated user-writable path. Now, the good news is I found such an example. This is hostname.exe. You might know it. It's a very boring process because literally all it does is tell you what your hostname is. That's all it does. In doing so, it loads a number of DLLs from the System32 folder. But strangely enough, it relies on the system root environment variable. So if I now start hostname.exe, but change that system root value, so normally it's C/Windows, if I now change it to C/temp/evil, I might be able to trick it into loading my variable. So this is how you do it in PowerShell. Just a few lines, just to quickly walk you through it. And the first one says, this is a new process block. The second line is where I specify hostname.exe. This is important because I don't change the path, right? This is where hostname is normally located. I don't move it, I don't change it. It's still signed and trusted. It's there. I then remove the system root variable from the stack. I then re-add it, change it to my path, and then the remainder is just making sure PowerShell knows how to run it. Right, demo time. I'm not going to paste in that code. And then hopefully, if I press enter, it's going to give us some visual confirmation of sorts that a malicious DLL was loaded. We also got Procmon running, so hopefully we get the proof there as well. So I am going to press enter. We've got a nice little pop-up box, message box. We got calc, because how else would you know we broke something, right? And then at the very top, you can see the hostname.exe in its normal location. But you can see that it loaded c/temp/evil, and it loaded my version, as is also represented by calc and the message box. Cool, so we broke something, but why would we care, right? So just take a step back. What is new about this? So we got a legitimate process that is present on every Windows installation to run malicious code. Not really malicious in this case, but as you can imagine, you can let it execute anything. The cool thing is that we didn't do anything really special, right? We changed a variable on process level, right? I didn't change the registry. I changed it on process level. There's nothing really observable in terms of command line, or you don't have to suspend the process or whatever. So from an EDR perspective, this is quite hard to spot. Yeah, and just to reiterate that, right? I didn't change the registry. I just started the process, overwrote the process level values, and made it do something bad. And yeah, to my knowledge, most EDR software, they don't look into this sort of thing, right? They might detect the module load from a weird location, but they don't check if the variables are changed, because we would do that. And as we've seen, a few lines of PowerShell can do this, but you can also do it with other built-in script engines like VB script or JScript. So if you have a macro that you can somehow run from a not updated Office version, you might be able to run it from there. And if you see Word spawning some legitimate process, SOC analyst or an EDR or AV might think it's fine. So yeah, this is an example in VB script. It's just a screenshot, but as you can see, it's just 3 lines of code. You create the shell engine, you tell it to update the system root, and then you say execute. And then simply run cscript. And then at the bottom, once again, we have evidence that it loaded my malicious version from the evil path. Sweet. So comparison, right, to the other ones, we called out a few issues with the other ones. Like DLL side loading, you need to usually move the executable or bring your own. It just means extra footprint. Good thing with this technique is that you don't need to move anything, because the process is already there. That's the whole point. Search order hijacking, limited options, as I will show you later. This was just one example, but I'm going to show you there's many more candidates. DLL substitution, input-based DLL jacking, all have their own limitations. But the good thing here is pre-existing applications, like lots of Windows applications or other common software, is vulnerable to this. You don't need elevated writes. It doesn't do anything really special from a detection point of view. And the real only footprint here is the planting of the DLL. Right? As a defender, how would you see this? Well, you might see a weird DLL in a weird folder. But when you think about it, like for DLL hijacking, that is sort of the premise, right? You're going to load a DLL. So if that is the only footprint, which you can't really work around, it's not that bad. In fact, because of how Windows works, you can even load a DLL from a remote path, like an UNC path or even a WebDAV path, which could potentially trigger all sorts of other rings and bells. But it means that even the planting of the DLL doesn't have to be an event. You could point it to a remote location through the environment variable, which is pretty cool. Cool. I think we're all right for time. I just want to quickly take you through the process, right? Because so far I've shown you one executable, so you might think, well, that's not really impressive. They could fix that, and then we're all good. No. So what I'm going to do is just show you how you can take this one observation and turn it into a wider approach. Now we can show there's more there. So what I've done is I took a sample, and it's a rather big sample, because I took every DLL that is in the System32 folder on a vanilla Windows installation. There's quite a few. There's like hundreds of them. But what I've done is for each and every one of them, I have created a fake version, like an implant. And basically, what that implant does is when it is loaded, the only thing it does, it is writing a file to disk. And that file is later on going to tell us what DLL was loaded by which process. So, right, first step, creating loads of implants. Then the second step is selecting my targets. So I took the same sample. I looked at every executable in the Windows System32 folder. And what I would then do is change one or more environment variable, right? I would run every process in that folder, point it to the manipulated implants folder, and then hopefully the last step, validation, as a result, right, these executions would load my fake files, my implants. Because they are loaded, they would create fingerprint files, and then at the end, hopefully you have a bunch of fingerprint files which prove which executables and DLLs are vulnerable. If you've ever done DLL hijacking, and some of you are red teamers, so you might have looked into this, one of the other ones, you know that is not without challenge. The main thing is that usually you don't really know how the DLL works, the legitimate DLL, or the process that uses it. Right? At least I don't have time to reverse engineer all these DLLs and executables to fully understand what it's doing. So if you're naive, like I was, what you might do is just create one generic DLL with a DLL main and just rename it every time and then hope that the target process accepts it. Now, most of the time this will fail. That's because programs execute their DLLs, the legitimate ones, to have certain exports and ordinals. Obviously, it has functionality as well. So if it breaks, it could be very obvious that the DLL wasn't loaded. User will be alerted, so that doesn't work. So what I then thought is, you know what? I'm going to create dummy functions. So I'm going to, for every DLL, I'm going to iterate what exports it has. I'm just going to, implement dummy functions. So literally, when you call the function, nothing happens, and then hopefully the DLLs will be accepted. But even then, right, if the functionality is not there, it might break the process, and it basically wouldn't work. So to maximize our rate of success, I'm going to use DLL proxying, or function redirection, which is a rather clever technique. It's a weird Windows-ism. Libraries have exports, right, which are public-facing functions. So this sumlib.dll has export A and export B. Usually, those exports refer to code inside that DLL. But for some reason, in Windows, you can define exports, but tell that the code doesn't reside in your own file, but in a different file. So the great thing here is that I could compile sumlib.dll. I can define export A and export B, but then whenever it's loaded, I say, no, I don't have the code. This version of sumlib.dll over there in the original path has the code, which is great because if I overwrite the environment variable and it loads my version and it's trying to rely on code in that DLL, it will always work because I simply point it to the original DLL. So it's rather clever, and because it still loads my DLL, I still get to execute code inside the trusted process. So that's pretty cool. And then finally, even with that, it might still fail because we always think of DLLs as pieces of code, but they often also have metadata, resources, right? Like I've seen applications having whole loads of images and cursors in there. So in order to, again, maximize the rate of success, I use something called resource cloning, which literally just copies all these resources to the cloned DLL file. We already did that. Cool. So to automate that, because as I said, we have hundreds of DLLs to go through, wrote this little script. It is a bash script. It runs on Linux, but it is using MingW, so you can also run it on Windows if you like. But basically, you point it to a folder, it goes over all the DLLs, and it does the thing I described. It would set up this function redirection, and it would copy the resources. So when it compiles it, what does it do, other than redirecting the functions? This would literally be the main function. And it's basically saying, if a thread is attached or a process is attached, call the function generate fingerprint. And this is my fingerprint function. Again, very simple. It takes the name of the DLL itself. It then uses the name of the process that loads it. And then it writes it to a public folder. So C uses public downloads. It's like user writable. So hopefully, when an executable loads my DLL, I will have a file called, I think I have it here, I'll have a file called name of the exe underscore name of the DLL, then the function, which is in our case always going to be DLL main, and then 0 or 1 indicates if it was elevated or not, which again in our case will always be 0. So the example I shown you earlier, if it loads, it would produce a file in the publics folder called hostname underscore msw sock underscore DLL main underscore 0. So once I've run this bash script, right, I have hundreds of implant DLL files. What I now need to do is run all the executables in system32 and point them to this folder. So basically what this is showing you is a PowerShell script that is basically just a for loop wrapped around the code I showed earlier. So go over every executable, change the system root variable, launch the program. We're not going to do anything fancy. We just run it with no command line arguments, nothing, no interaction. And yeah, hopefully it will load the DLL file, and we end up with a bunch of TXT files in my downloads folder. So after doing all this and running the PowerShell code, this was my downloads folder. You can see that there's quite a few in there. Again, you recognize the pattern, right? So say in the middle, we have certrack underscore csc UI.dll, meaning that I executed certrack and it loaded my version of csc object.dll. As you could tell from the scroll bar, there's quite a few DLL files in there. So this means all these combinations are unique patterns, unique combinations that you could use with this technique. So before I go to the results, if you want to do this yourself, because I only did system32, right? You could run it against other software like, I don't know, Microsoft Office or your own software. I already did the hard work, so you can literally clone it from my GitHub page, and it's already doing the function redirection and the function or the resource cloning. Right, the findings. So I tested it on Windows 11. You might have recognized it from the screenshots. Of all the executables I run, I found 82 to be vulnerable, and there were 91 unique DLLs. So there's a couple that are very popular, like there's one DLL I think that has like 20 executables that try and load it. So combined, we nearly have 300 unique combinations out of the box on Windows that you can use with this technique. Now, third-party software, right? So I tried a few things just to sort of like, is it just Windows that's really bad, or is there more? So I tested Windows or Office 2021, and all the big ones like Word, PowerPoint, Excel, all of them at least tried to load one DLL using the system root variable. So once again, starting WinWord with a manipulated variable might trick it into loading malicious code. I tried the big browsers like Edge, Chrome, Firefox. Again, all of them, at least one DLL is loaded by simply changing one of those big environment variables. And the possibilities are endless, right? Think about an office setting. You will have something like Slack or Zoom on there. Again, they all have this, I would call it flaw. It's not really vulnerability, right? But this flaw where it relies on a variable that you can trick it into do something else. So my point is, right, I have published all these unique combinations, so you can look for it. But my point here today is that it's not really about the individual results. Ultimately, it's about like this technique. As you can see, like there's so many possibilities, and this is just the stuff we tested, right? What about other software that we didn't test? So what we need is not the individual results, but sort of a mindset from a defender point of view, or even an offensive point of view, that this is just beyond just a few examples. This is a bigger, wider pattern that's just on Windows, that you will see on Windows over and over again. I think we're still good for time. So let's take it further, because so far I've only talked about execution. So you need an initial foothold, and then you just execute code. But can we take it a bit further, like persistence maybe? The thing is, we need to start a process, but we need to override the environment variable, right? We don't want to change the registry, so how do we do that? To my knowledge, you can't do that with a shortcut, right? You can't create an LNK file and tell it to run something with a change variable. You could do it with a script, but that's not really persistence, is it? So one thing you could do is look at services. These are once again defined in the registry. This is the printer spooler service, again, enabled by default on Windows machines. And one of the very under-documented options there is environment.
You won't see it in any of the pre-installed services, but you can define it yourself. And as you can imagine, right, or as the name suggests, you can specify your own variables here. So what do you think happens if I now restart the printer spooler or if I reboot my machine? Let's find out. We got it to load my version. So I changed it to temp Windows 64. And once again, it did that. But if you've have a good eye, you've seen now that it loaded it as system, whereas you only need admin permissions to change that part of the registry. So whilst this is not proper privilege escalation, it is still interesting, right? Because we all know a normal admin can do a few things that can't do a few things that system can do. And it's pretty persistent, right? Because every time your machine reboots, it will do this. It still loads the normal printer spooler executable. So if your EDR is not monitoring that variable, you might completely miss it. All right, what about better privilege escalation, right? Can I somehow trick a user into accepting a HIJACK prompt, user account control, and let it run my code with extra privileges? Now, this is where something interesting happens, because you have two main ways of starting new executables in the Windows API, and both are slightly different. One cannot run programs that require elevation if you have lower privileges. Excuse me. And the other one can elevate itself with a HIJACK prompt, but that one does not take environment variables. So this is in PowerShell. If you try either way, you'll see you get different errors, but bottom line is it won't let you do it. This seems to be a very conscious decision by Microsoft, sort of like as a result of all this path environment variable drama, to not let an executable that has higher privileges than its parent to inherit the environment variables. So that kind of makes sense, right? If you start a new process and that is with admin and you're not admin, it sort of resets the environment variables. So it looks like the people in Redmond did do something right when it comes here. So this, to be honest, prevents a lot of trouble that would otherwise have occurred. So it's quite good. I will note, though, there are, I know of one at least, there's one or two processes that sort of overwrite this behavior. So they would start as with HIJACK, and then the first thing they do is sort of like copy the environment variable values of its parent. So they sort of manually circumvent this. So there, even with this, there is still scope for some tampering, but it's not as widespread as it would have been otherwise. So well done. Countermeasures, right? What could we do to prevent this from either a dev point of view, or if you a blue teamer or a defender, what can we do to stop this or detect this? As a developer, right, because every program, doesn't matter how big or small it is, could be susceptible to this. Please, 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 if you can, use absolute paths. I know that's not always easy, but for things like System32, there are beautiful Windows API calls. That means you don't have to rely on these variables, which, as you can see, are very easily tampered with, but give you something that the operating system, the kernel, has approved, if you like. Sometimes you really can't go around this. If you have a portable application, right, you're always going to load something that is next to you. If you do that, please, if you can, try and validate the DLLs, right? Sign them, check them before loading them. There's loads of functions there that don't have to compromise on performance. It just makes it a lot less likely that someone can abuse it for bad. From a detection point of view, I already touched on this, right? EDRs have a hard time spotting this. Look for the changed process level variable. I don't know of any EDR that does it. You could still monitor DLL loads from weird locations. For the specific one we looked at today, system root. System root goes to C/Windows, whereas usually the DLL is in C/Windows/System32. So that means if you abuse this trick, right, all the paths I've shown you today, C/Eval, always included at the end /System32. So for this specific variable, it's very easy to detect by just looking for System32 folders that are not under the Windows folder. It turns out it's rare. It's not zero. It's like there are some documented cases where that happens, but System32 folders not under Windows, very rare. So from a defensive point of view, it's a simple, low-hanging fruit way of doing it, but it won't stop everything because I've only looked at system root. And finally, look at known DLL hijacking instances. Again, we've seen, right, that it's too many to look at them all. But if you know a certain DLL hijack has taken place in a past attack, I think you'd be crazy not to look at it, right? It's the same with lol bins. Like you're not going to say, oh, there's too many of them, I'm not going to monitor them. No, if you know something has been abused, of course you're going to look for it. If that all fails, ultimately, right, if you load malicious code, that malicious code is going to do something stupid, right? It's going to reach out to the internet, to some weird C2 framework. It's going to spawn new processes. If you see hostname.exe spawning a process, that is weird. If you see your printer spooler reach out to a Chinese IP, that could be weird, right? So ultimately, you might miss the DLL hijacking, but focus on everything that follows, would be my recommendation. We have a few minutes left, and I want to talk about the future. So we've seen a new type of DLL hijacking today. What does that mean? Well, I think the key message here is that DLL hijacking is here to stay. Because even for all the other variants, right, if we somehow magically fix them all today, attackers would still be able to use it tomorrow, because you could bring in old versions and use the same tricks. So somehow we need to learn to live with DLL hijacking. Again, there's both offensive and defensive. So to help with that, I last year launched this project called HIJACK LIBS. It's a open source collaborative platform where you can document, or where I document a list of observed DLL hijacking instances. So this platform contains all the environment variable-based hijacking that I talked about today, but also known sideloading instances, phantom DLL sideloading and search order hijacking. So it records all these DLLs, and for each DLL, it tells you what types of hijacking it is susceptible to. It tells you where the DLL normally is located, right? Legitimate instances. It tells you what executables we know are vulnerable to loading that DLL in a weird way. And if you're a defender, it even contains some basic detection logic in the Sigma language. So let's take a look at what that looks like. This is the homepage, so it shows you some new entries. You can then look up a DLL, right? Imagine you do an investigation or you're looking for a DLL to hijack. Here it tells me it is susceptible to both sideloading and search order hijacking. It then tells me some resources if I want to read more about campaigns it's been spotted in. It tells me in this case it's normally located in system 32. It then tells me these 3 executables are vulnerable. And this Sigma rule then helps me detect it, right? Sigma you can convert to your vendor language of choice by converting it. What else is there? It's also categorized by vendor, right? So you could look up a certain vendor if you know, say, VLC software is running on your target environment. Here it gives me a good example of a VLC binary that has been used in the wild. It even gives me a hash sometimes if that is available. And again, here I can see it is a sideloading entry. So from a defensive point of view, you could check if you find that DLL in a weird location, or offensively, you could use that to build your own. This is a list of all of them, and as you can see, there's lots of them and many different combinations. So does it make a difference, right? I've been running this for a few months now. Did it change anything? I got 2 or 3 tweets here. On the left-hand side, a blue teamer, and on the right-hand side, a red teamer. The blue teamer says this is great because I load these DLLs. There's a feed available, like a CSS file or a JSON file, and I port them once a night and then baseline them because noise will happen. But then it's a really easy, low-hanging fruit way to find bad stuff. So great. Then we got the red teamer. I believe in his profile he says he works for Mandiant. He says, you know what? I basically look up a DLL file on this platform. And if it is there, I'm not going to use it. So I basically use it to check if it is a commonly known one. And if it isn't, that's, for me, the validation that I can use it. So if you're blue team, this is a wake-up call. We have to add more things to the project. If you're a red teamer, this is a good wake-up call. Double check if it's on the project, because then you might be more easily found. So yeah, that is my message for today. I really hope that if you know about DLL hijacking instances, of course, you do contribute. We have had about a dozen contributors there from all parts of the industry. It's community-based and open source, so feel free to also recommend new things.
even if you haven't discovered the DLL hijacking yourself, right? If you find a report or something else, feel free to open a pull request and join the project. That was it. I hope that was useful, and thank you very much. I think we have a minute or two for questions. Yeah, go for it. Yep. It doesn't. It's just on, say, Mac and Linux, environment variables work slightly different. And in my experience, I know there are Linux processes vulnerable to this, but they usually don't rely on variables as much. So they wouldn't load DLLs from like your home path, right? But they would just do it from user/bin. So that's hard coded. So then you don't really have this issue, if that makes sense. But good question. I like it. Yeah, that was a good question. So just to repeat that, so can you use the DLL to call it something to bypass UAC? Yeah. Yeah. 100%. So as long as it doesn't require extra elevation, which it doesn't in this case, right? Yeah, you'll be able to do that. Again, it might do stuff that that process normally doesn't do, so it might stand out. But yeah, there's nothing stopping you from doing that. So you're right. You could take it one step further.